Good evening, everybody, and thank you for joining us today. I'm here to welcome you to the 2026 Mandel Lecture in Astrophysics. As it says on the slide, my name is Brian Gainsler. I'm a professor of astronomy and astrophysics at UC Santa Cruz, but I am speaking to you tonight in my capacity as the university's Dean of Physical and Biological Sciences. And I'm very proud that the Division of Physical and Biological Sciences has hosted the Mandel Lectures since their inception in 2014. So the goal of the Mandel Lecture Series is to promote public awareness and appreciation for astronomy. And if you know anything about all the different things that you've heard about at the Mandel Lectures over the years, the Mandel series has very much accomplished that. So the Mandel Lectures have been made possible through the generosity of Steve Mandel, who is sitting right in the front corner here. Thank you, Steve. So when I describe Steve to people, I think the best explanation, how I like to describe Steve is he's a gentleman scientist. So back in the 1700s and 1800s, there were these individuals scattered across the world who weren't professional full-time scientists working at university, but they were people who were smart and they were curious and they had broad interests. And many of these people made genuine discoveries across multiple areas. So probably the most famous gentleman scientist was Benjamin Franklin, who you might have heard of. And he wasn't just the founding father of the United States, but he was an amazing scientist. He invented lightning rods, he invented bifocals, he invented daylight savings time. And very much in the tradition of Ben Franklin, Steve has made major advances in multiple scientific areas. He's worked on microscopic diatoms, he's worked on glaciers, he's worked on wildlife ecology, and he has made significant contributions and discoveries in astrophysics. So Steve is a true polymath. He's a tireless supporter of UC Santa Cruz, and he's an all-round wonderful human being. So please join me in welcoming to the stage my friend and my colleague, Steve Mandel, who will kick off tonight's proceedings. Welcome, Steve.
Well, thanks, Brian. And I'm just going to stay up here for 2 minutes, which usually ends up being 20 or 30, but I'll try to be real brief here. And just 2 things I want to say tonight, and one is thank you. First of all, this is truly takes a village to make all this happen. And we had a team of graduate students. Are any of you in the audience here? They were out at the tables checking you in, so they're stand up, graduate students. Round of applause. These people work so hard. Thank you. And I want to thank all of you for attending tonight and supporting astronomy and astrophysics at UC Santa Cruz. We have a wonderful speaker, and Jonathan will come up in a second and introduce her. The second thing, if you're interested in this, you might be interested in this. And there we go. This little poster, there's flyers out there that you can take on the way out. And there's going to be an exhibit downtown at the MA. If you don't know what the MA is, it's the Museum of Art and History in downtown Santa Cruz. It's called Beautiful Universe. And I've been working on this with one of the astronomy professors and a couple of my colleagues. And it'll feature about 25 photographs taken from the observatories that I operate in California, Chile, and Australia. And the whole idea is to have people come in, behold the beauty, the art of the universe, and think about the science. And so on the weekends, the 2 weekends that this covers, we'll have graduate students and some faculty there to help interpret, answer questions, and give you any information they can about the images that you see. So I hope you can do that. It's the last 2 weekends of May, and once again, there's a flyer here. And I took a risk and put my email address on here, so feel free to send me spam or whatever else you want to send me. It has been a great privilege to sponsor these lectures, but I have to give my wife Carol Foote credit. Carol's sitting up here. We do this together, and we've been married how long? 42 years, 43, something like that. And any of you who have been married a long time, you know who the boss is. So we have to thank Carol also for this. So thank you, dear. Anyway, I want to turn the microphone over to Jonathan Fortenay, and Jonathan is the Department Chair of Astronomy and Astrophysics, and he's going to introduce our speaker. So, Jonathan?
Hi, everybody. It's great to be here for another Mandel lecture. This is really one of the highlights of the Department of Astronomy and Astrophysics every year, is getting out into the community and seeing everybody and telling our Santa Cruz community about astronomy. Really like to thank the generosity of Steve Mandel. It's really through Steve and Carol that we're able to have these events. And I wanted to mention that you also can help to support our department. Your gifts really help us do public events and also support our work on campus, funding for student projects, for student travel. Astronomy is sort of unusual amongst the sciences, where historically benefactors have supported this field and has led to a lot of fantastic discoveries over time. And so your gifts really make an enormous impact. So here's a QR code you might want to scan. This will be up later as well. So thank you for any support you might be able to give. I'll move on now by introducing my colleague, Alexie Leauthaud. Alexie and I have been colleagues for about a decade now here on campus. She leads a research group that explores some of the deepest questions of our universe, the questions of the evolution of the largest scales, cosmology, and then also how galaxies form, and the relation between the largest scales and how that informs our understanding of galaxy formation and evolution. How dark matter is distributed in our universe, and also the nature of dark energy and how that might change over time. And these are things I'm sure you'll hear a fair amount about tonight as well. In addition, Alexie is really a world leader in her field. She's the co-spokesperson of DESI, the Dark Energy Spectroscopic Instrument. This is a major international survey. They just had a big press release today. So if you Google DESI, D-E-S-I, you'll learn about that. I'm sure Alexie will also be mentioning that today as well. Their results of last year and this year are based on surveys of mapping tens of millions of galaxies in our universe. Of course, we live in the Milky Way, one galaxy. But DESI's been mapping tens of millions of those to learn about the nature of dark energy in our universe and how that might actually change over time. Beyond her leadership in cosmology and the largest scales of our universe, she also has her own very interested and growing research program in sustainability and understanding climate change on the Earth. So she leads a program called Seed Spoon Science, which supports Spanish-speaking STEM undergraduates, connects with local families, and promotes urban gardening. She's also a founding member of the UC Santa Cruz Climate Action Now group, and she's organizing North American collaboration of US and Canadian institutions to address institutional barriers that slow meaningful addressing of climate change. And that's a growing importance to Alexie's research, and that she's really incredibly unusual in being able to both do astronomy and climate change. So in so many ways, Alexie embodies the bold, boundary-crossing spirit we like to have at UC Santa Cruz. Someone who thinks at the largest scales, but also is thinking about our own planet and how to treat it well. And so let's join me in welcoming Alexie up onto the stage.
Thank you, Jonathan. Thank you. Thank you, everyone. I'm so excited to be here tonight. Let's do a little mic check. Mic check. All right. I like to walk around on the stage. So I'm Alexie. I'm here to take you on a journey tonight. Did they tell you needed your hiking boots for this journey? This is a really big journey because we're going to journey across the entire universe. So without further ado, oh, sorry, wrong direction. We're going forward in time. Time is one directional, by the way. So we're going to start with a brief history of our universe in 1 minute. Okay, so our universe, I hope you got the quiz correct earlier. Our universe is how old? 13 or 14 billion years old. That's correct. It's written down here. So let's start at the beginning. We think the universe started with a Big Bang. Following the Big Bang, it had a phenomenal period of expansion called inflation, over here. Following inflation, the universe was dark. There were no stars, no galaxies. We call that the dark period, the dark ages. And then the first stars in this diagram come about around 400 million years into the evolution of the universe. However, recent work from my colleague, Brant Robinson, and Courtney, down here in the corner, PhD candidate in our department, have found, using the James Webb Space Telescope, galaxies as early as 300 million years old. So 300 million years after the Big Bang, not only were there stars, but there were fully formed galaxies. So that is a new and recent discovery that is puzzling the community. So this diagram needs to be revised. Following the formation of the first stars, we get the formation of the first planets, and then we get a phase of accelerated expansion, which is going to be one of my big topics today, and that's us here, sitting over here on Earth. That's the history of the universe, folks. And go home now. Talk's done. But let's dive into some deeper mysteries. So what are the largest unknowns in astrophysics currently? The first one is the nature of the Big Bang. We don't understand the physics of the Big Bang. I don't study the physics of the Big Bang, but really we don't have a good understanding of how and why our universe originated. Secondly, oh, I can't walk too far away. What is the physics of inflation? This early period of incredible expansion that took the universe from very small scales to very large scales is very poorly understood. Why do we live in a world with very little antimatter is another one of the great mysteries. What is dark energy? That's going to be one of my themes for today. What is dark matter? Another of my themes for today. These are two different things, and I'm going to try to convince you that these are two different pieces of physics. Is there life beyond Earth? Another of one of the great mysteries in astrophysics. And finally, are there other universes? So there's lots of very exciting questions to work on. I'm seeing some young folks down here. There's plenty of big questions open. Now, I like to start by giving you a sense of cosmic time, and then we're going to talk about cosmic scales, because here on Earth, it's very hard for us to grasp the large scales of the universe. So let's start with cosmic time. I love this. It's called the cosmic calendar. It takes those 14 billion years and it puts it on a human one-year calendar to try to give us a sense of cosmic time scales. So the Big Bang is over here, January 1st. You have to wait until September for the formation of the solar system. Following the formation of the solar system and the Earth, one thing that's very amazing to me is life appears very rapidly after the formation of Earth. And then we have to wait for a very long time. The 30th of December is when the dinosaurs go extinct. Here, I want you to remember this time, because it's going to, believe it or not, come back in the talk. 8 p.m., humans and chimpanzees split. So now you're starting to think about New Year's Eve dinner. You're probably running late. We're usually running late, trying to get everything ready. Well, all of modern human history takes place within the last 10 seconds. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Done. And your lifetime is literally the blink of an eye. It's a quarter of a second. So that puts us in perspective in the cosmic timescale. Now, I'd like to also give you a sense of cosmic sort of distances and number of galaxies and number of stars. This is an image taken from the James Webb Space Telescope, a recently launched telescope that's been making groundbreaking discoveries, and it's just beautiful. But what I really want to do is give you a sense of the scale of this image. So what I want you all to do, without fail, is to put your finger up and look at your finger. Okay, so you're gonna look at your finger. So the size of your finger, and I want you to do this actually when you go outside. When you see the full moon, you can cover the full moon with your finger. The full moon is about half the width of your finger. Okay, so that's the full moon. And this image is about 6 arc minutes across. So this image is the little red dot on the moon. So if you're still holding, you're supposed to still be holding your finger up like this. Okay, so you visualize the red dot, and that is the size of the picture that I'm showing you now. This picture has about 200,000 galaxies. Now, Milky Way is one galaxy, but there are many other galaxies. And each galaxy has about 100 billion stars, and each star has on average 1 or 2 planets. So I don't want to stand up here and do the math. We've got to multiply these zeros together. So we're going to take 10 to the 9, 10, 11, 12, 13, 14, 15 possible stars and planets within that little red dot on your finger. That's how large the universe is. And then I want to tie that in with the question of finding alien life, life beyond Earth, because for many people who work in this field, when you see the sheer number of galaxies and the sheer number of stars and the sheer number of potential planets, the idea that life exists elsewhere beyond Earth, it just seems obvious. But that doesn't mean that we will necessarily find it. Life may exist, but it may be too far away or too distant for us to, or too difficult for us to detect. Okay, so that's cosmic scales. Now, I want to talk in one slide about life beyond Earth, and to do this, we're going to play the alien guessing game with my colleagues. So I'm privileged to work at UCSC, which has a premier, sort of the world leading centers for studying planets outside of our solar system. And so I was lucky enough to be able to query my colleagues and ask them these questions. Now, they didn't know the answers to their colleagues' questions when I asked this, so this is why it's called the guessing game. Okay, so Professor Skemmer, Professor Battaglia, Professor Fortney, who you met, and Professor McIntosh. So the first question I asked is, when are we going to find alien life? What do you think? What do you think? Anyone? All right, here's what the experts said. Andy Skemmer, a younger Andy Skemmer, said 2030. However, given, this is very serious, he told me, given the current funding attacks on science, this is going to be delayed, and he said 10 years or more. And this is from optimistic to, going too far ahead. Optimistic to pessimistic, by the way. So Jonathan is at 2070. He may be retired by then, I don't know, maybe that'll be your grad students. And Professor McIntosh said 2,100 or maybe thousands of years. But notice that no one said, we don't believe there's no life out there to be found. It's a question of when it will be found and how it will be found. So the next question was, how will we find it? And my colleague Andy said, using the scientific method. And at first I was going to make fun of Andy, and I was going to say, well, Andy, we're not going to use divination to find extraterrestrial life. But then I thought about it more, and I thought, given the attacks on science and the way the funding is going, and we'll come back to that later, it is entirely possible that in 20 years we'll be doing this with divination. So maybe this is actually quite a profound answer. But my 3 other colleagues all converged on spectroscopy of exoplanets and looking at their atmosphere. So looking for signs of life within the signatures of light. And then finally, I asked them, what kind of life will we find? So plankton, microbial life, bacteria, and plants. So everyone thinks we're going to find some kind of life. But I'm going to quibble with my colleagues, because I disagree, and I think there's a very human bias in here. They've missed an entire category. Which category have they missed? One of the kingdoms. I heard it. Oh, I thought I heard fungi. They missed fungi. And if you've been to the movies recently, you know that fungi eating the sun is one of the first signs of alien life that we're going to find, as well as xenon life forms. So my question for Jonathan is over here is I really hope your spectrographs are going to detect fungi and xenon. All right, moving on. What is the universe made of? Well, everything that you know and love and hold dear, water, food, stuff that your bodies are made up of, hydrogen, helium, all of that is made out of what we call regular matter. It's only 5% of the universe. The rest of the universe is made up of a whopping 26% of dark matter and an even larger 70% of dark energy. So we have very little understanding of what makes up most of the components of the universe, and that's going to be part of the talk for today. So I'm going to start with dark matter, and then we're going to talk about dark energy, and then we'll talk about some of the challenges ahead. So let's start with dark matter, and I'm going to have a slide explaining how dark matter is different from dark energy. So first of all, dark matter, as the name implies, is a form of matter. It's a mass. It's probably a particle. It's not something that you can touch because it doesn't interact with regular matter, but it is some kind of thing. It's 30% of the mass and energy in the universe today. It's unambiguously detected. There's scientific consensus on the existence of dark matter, and it earned a Nobel Prize in 2019. But we have not detected it currently. And we have good ideas, but we don't know what it is. I think I need to stand over here. So the discovery of dark matter was cemented in the 1970s by Vera Rubin, a pioneer in this field. And she studied the rotational speed of these spiral galaxies. So these spiral galaxies spin, and we can measure the velocity at which these spin. And she found that these galaxies are spinning a lot faster than they should be, given what we see. And so she inferred that there was an unseen mass that was called dark matter. So that was the discovery of dark matter. And since then, we've been studying it from many different forms, but we still don't know what it is. So dark matter is some kind of invisible matter. We know it's there because it interacts with gravity, so it causes galaxies to spin faster. It has lots of gravitational impacts on the universe. We have a lot of good ideas. So there's a lot of strong candidates for a dark matter particle. In fact, many colleagues at UCSC work on such dark matter ideas. So we have a range of ideas for what dark matter might be. Some of the things in the physics department that people have worked on are, Professor Dine has worked on ideas surrounding something called an axion. This is a dark matter candidate. My colleague Profumo has some really cool ideas, thinking that dark matter might be a very small, lots and lots of very small black holes. And then Yeltima over here has worked on trying to figure out whether dark matter is a sterile neutrino. So the main point here is that there are lots of good ideas out there, and it's a question of figuring out which of these ideas is the correct answer. How are we looking for dark matter? We have two ways of searching for dark matter. One is from the Earth, and one is from space. So on Earth, we build detectors, and we try to find evidence for dark matter hitting these detectors. It's called direct detection. And then over here, we build telescopes, and we look out to the distant universe, and we try to figure out the impact of dark matter on various observations. So this is the one I'm going to talk about now. One of my programs relates to dark matter. So the particular program that I created with a colleague from Princeton, my co-collaborator, is called Marion, and it studies dark matter in tiny little dwarf galaxies. And so this is our logo. We named it after Maria Silvia Marion, who was the first female entomologist. And she studied tiny insects, and we thought this was analogous because we're studying tiny, tiny little dwarf galaxies. These are images of some of the dwarf galaxies that we are studying. These are the images right here. You can see they're very small and they're very blue. And these kinds of galaxies have a lot of dark matter in them. And because they have a lot of dark matter, they're really good candidates to try to measure similar things that Vera Rubin measured with this rotation over here. So in essence, we're conducting a very similar measurement to the original discoveries in the 1970s, but using a much larger data set and new techniques and testing new ideas. But essentially the methodology remains fairly similar. These are two graduates. Ife graduated and is now a postdoc at the Lawrence Berkeley Lab, and Zhao is a PhD candidate. And these are two members who are starting this dark matter in tiny galaxies. This is the only complicated figure that I want to show you. This is the amplitude of dark matter around these tiny galaxies as a function of their distance from the center of the galaxy. And we were extremely excited to see this figure because it took us 5 years or more to get there, including this. My poor grad student at the time went to Keck observatories 3 years in a row and got snow. And so that was a dampener. But after many years, we have been able to measure the dark matter around these galaxies, and it's a very beautiful signal, and we're using this to try to understand what kind of dark matter is around these galaxies. Clicker isn't working. All right, so now I want to talk about dark energy, one of the other big mysteries. Hello? Maybe I've got some dark energy in my laptop. So dark matter, if you remember, is a kind of particle. Dark energy is a form of energy, and it behaves very differently from dark matter. It is the dominant mass plus energy in our universe, representing 70%. And one of the key things that it does is it accelerates the expansion of the universe at late times, and that's how it was discovered in the 90s. It earned a Nobel Prize in 2011, and it is one of the deepest mysteries in physics today. But don't confuse dark matter and dark energy, they're two different things. So I have the honor of serving as co-spokesperson for DESI, the Dark Energy Spectroscopic Instrument. That means that I'm responsible for the scientific coordination of the results from this team, but everyone else does all the hard work. And my co-collaborator on this is Will Percival from the University of Waterloo. And then I wanted to mention my colleague, Connie Rockesy from our department, is the co-instrument scientist for this program. So UCSC has a large involvement in this effort. But this is 900 scientists distributed across the world who have come together to study dark energy using a telescope at Kitt Peak in Arizona called the Mandel telescope. We had a press release today, so you may read about us in the news. The press release was about the fact that we've completed our original 5-year mission. So we were budgeted and planned for 5 years. We ran ahead of schedule, and we got more galaxies than we said we would. So we ended up getting 47 million galaxies and quasars. This is the map from the completed survey. This is distance going back in time. So we are here at the center, and this is going far away and also looking back in time. And some of the earliest galaxies that we look at, the light from those galaxies is traveling 11 billion years to get to us. This is the largest map of the universe ever created. So you're looking at the largest map that humans have ever created of our universe at large. Now I'm going to show you a flyby. So this is a more pretty picture of this flyby. So every point in here is a galaxy. It's a real galaxy that we have measured. And so now you're flying through the universe and you're seeing lots of different kinds of galaxies. You have beautiful spiral ones, blue ones, red ones. So that's what our universe looks like if you are flying at many, many, many times the speed of light. So I don't want to go into detail about how we make our measurements because it gets a little complicated. All I want to say is we take this 3D map and we look for rings. These are signatures that date back to the very early universe of what we call an acoustic oscillation. It's essentially a sound wave. And by mapping these galaxies, we measure these sound waves. And by measuring the sound waves, we measure dark energy. I've skipped a few steps there, but you can come and ask me afterwards. We've had 2 papers that were top news in the media 2 times in a row. Here are 2 papers. If you care about citations, which you shouldn't, These papers have been cited at an amazing rate. The top one here is 1,500 citations, and the second one almost has 1,000 citations, because they're making potentially fundamental discoveries about dark energy, and therefore they're generating a lot of interest in the community about trying to rethink what we think about dark energy. Over here, I'd like to highlight this one because we were listed among the best inventions of 2024, sandwiched in between AI. But we're still doing real science. So I want to briefly tell you why these results have been so exciting. So we think that our universe, we think that it's governed by something that we call the lambda cold dark matter model, known as lambda CDM. That's our model for how we think the universe evolves and operates with time. The dark energy is this parameter lambda in this lambda cold dark matter model. This is a picture from a museum wall in the Netherlands with this equation at the bottom. This equation is the Einstein field equations. And over here, this part of the equation tells us about the geometry of space-time. And this part of the equation tells us about mass and energy. And essentially what this equation tells us is space-time tells matter how to move, and matter energy tells space-time how to curve. That's the essence behind this equation. But I want to highlight here, if my pointer will work, that there's this lambda not lambda representing dark energy. And to date, everyone has operated on the assumption that lambda is a constant. It's a single number, and the latest results from DESI suggest that it may not be a single number, and it may be, in fact, quite a bit more complicated. So the findings challenge this current paradigm of our fundamental understanding of the universe. I'm going to show you one diagram here to try to convince you that this is true. This is time. This is today. This is going back in time 10 billion years. And this is the value of dark energy here on the y-axis. Now, the lambda CDM model, that sort of standard model that we've been operating in, would be this constant line here. But these are the DESI data, and you can see that the blue line doesn't align with the constant yellow line. That's the mismatch. And then secondly, the second reason these results have generated so much attention is because if you had asked theorists if we were to discover a dark energy that's not constant, where would it fall? They would have said it's going to fall up here in this quadrant. But the DESI results actually fall in a regime down here that is very unexpected theoretically. So dark energy is not only varying with time, we call it dynamical dark energy, but also it takes on unusual values. So those are, in essence, the results from DESI. Now, I've told you that dark energy causes the universe to accelerate at late times. So if we're now going to an understanding of dynamical dark energy, where dark energy changes, that's going to impact what's going to happen to the universe in the future. So what does this current DESI understanding tell us about the future of our universe? So this is time, this is the Big Bang, this is the scale of the universe, and different dark energy models might lead to a big rip where the universe destroys itself, or a big crunch where we have a new Big Bang. The constant dark energy line is here, and the current DESI results suggest that we're maybe headed more in this direction with a slowing down of that acceleration. But the truth is, without a physical understanding of dark energy, we can't really predict the future any better than that. I wanted to return to one of the fundamental mysteries of the universe, inflation. I mentioned that there's this very early phase in the universe where the universe expands at a phenomenal rate, and that's called inflation. Another point of interest is that we now have two phases in the universe where the universe accelerates in unusual ways. And so an open question is dark energy at late times and inflation at early times connected? That's another fundamental mystery. On the one hand, they have similar behavior because they're both accelerating the universe. But on the other hand, they're very different in magnitude. This one is extremely powerful, and this one is less so. This one operates in 10 to the minus 32 seconds. and this one operates over billions of years. So the timescales are mismatched, but some people think they may be connected. All right, so I want to move along to the biggest challenges that lie ahead. And the biggest challenges I'm going to divide into 3 categories: scientific challenges, political challenges, and what I'm calling our greatest challenge yet. Scientific challenges. It is not obvious to me that we are going to solve dark matter and dark energy. I would love to think that we will, but I think we also need to be realistic about the challenges that lie ahead. So what are some of the key barriers that I think that we face? Recently, I wrote this paper with Adam Rees, 2025, about the challenges in terms of trying to solve dark energy. One of the ones we talked about in this paper was about humans working together. So I've noticed within the DESI team, some of our best groups are people, groups that are of order 10 to 20 people working on a common problem. The dark energy problem could ultimately prove to be so complex that we need to harness the power from multiple different groups working across multiple different data sets that have different policies and different politics. And I've already seen challenges within the group about trying to work with other groups. And so it may just be that putting the human brains together to work on these complex problems may be one of our limiting factors. Another limiting factor is what I'm going to call the unkind universe, which is that really, if you step back and think about it, what I've proposed here, that we have a dark energy and a dark matter, and it's a particle and it's an energy, that may be too simplistic. That's the most simple thing that you could assume. But what if the universe is much more complex? Look around. Earth is complex, the solar system is complex. And so what if we have multiple kinds of energies and multiple kinds of dark matter, and dark matter and dark energy interacting together in some funny way? Then it may be that the physics is just too complex for us to figure out, giving our limited view of the universe. Which leads me to the third point. Another barrier could be that here on Earth, we only have a limited view of the universe. There's only so far we can see out within our local bubble. And in fact, DESI over here, in some ranges in distance, we've already looked at basically as much as we can see. And so there are certain measurements we know it's pointless to repeat them. We're not going to learn anymore. We need new ways of thinking about the problem, but we may ultimately be limited by the size of the visible universe. And then finally, some of the questions that we are interested in, we may be limited because there's no way of testing these ideas. So I'm going to bring up 2 examples. These are 2 of the fundamental questions that I raised in the beginning, where there's almost no way of testing these ideas. Even though they're beautiful ideas, we may never be able to confirm them. One is this idea of inflation, the fact that the early universe went through a phenomenal expansion rate within 10 to the minus 32 seconds. That was so long ago, and there's so little signatures of it today, it may be that we can never really determine if that was the situation. And finally, another of the great mysteries, are there other universes? There are actually theoretically very compelling reasons to think that there may be other universes. This goes under the name of the multiverse. But there's almost no way of testing that idea. And so that may just always remain within the realm of a really cool idea. Now, however, I did say that there were almost no ways of testing inflation. But scientists love a good challenge, and so we are fortunate to be working on the next phase of DESI, called DESI 2. We're in the planning phases of that will start in 2028, and we'll go beyond the question of dark energy, and we'll be trying to probe this early phase of inflation. There are some signatures, and we're going to try to go after those signatures. However, we also face political headwinds. Andy Skimmer's comment on slide 5 helped us lead into here. And I fully agree with this statement from a colleague who says it's been an extinction level event for science. And I'm here to confirm that that is indeed what's going on. This is a figure made also by my colleague Andy Skimmer, showing awards from the National Science Foundation. This is where we get a lot of our funding over time. So you are aware that last year the president proposed extreme cuts to the scientific budgets. Ultimately, Congress still allocated that money, but the truth is that money is not getting out to the scientists. So this is how much money got out in 2025, and you can see there's a huge discrepancy with previous years. And this is the award funding in 2026. So the president's attack on science has a direct impact, despite Congress's allocating the money. I have been extremely concerned in particular with the hard hits to health and the environment, and the systematic dismantling of the National Oceanic and Atmospheric Administration, NOAA, as well as a premier research center for climate change in Boulder. And then the president just proposed a budget for 2027, which is nothing short of catastrophic. It would completely eliminate NOAA, and the proposal is to cut the NSF and the EPA budgets by 50% and NASA science cut by 45%. So, if this comes into play, Jonathan will probably be using divination to search for alien life. One consequence of this is that the brain drain is underway. Other countries have seen this, and it's a fantastic opportunity. Fantastic opportunity. So Canada has a $1.7 billion fund to attract researchers looking to move abroad. I know people who are applying to this, and I know early career researchers, postdocs, and grad students that are looking at these opportunities very seriously. China has a new program to relocate scientists who have lost funding. Europe has a program, I've seen this widely advertised within emails and other media. The president of Aix-Marseille, which is one of my alma mater, by the way, said that if the Republicans win in the midterms, they're going to need a whole new program because they'll get so many more applicants. It has been estimated that the impact of these funding cuts is about $1 trillion over 10 years. That's a big economic impact. And guess who the biggest winner of cutting science funding in the US is going to be? It's China, because China is massively investing in science, and it's attracting lots and lots of researchers. And so if we continue down this path, China will become the premier research country. Third challenge is what I'm calling our greatest challenge yet. And so this leads me into the third part of my talk, and our greatest challenge is this. What is this? I can pick on you all down in the front row. Anyone? What is it? Survival? What do you think?
A jacket?
It does look like a jacket. Oh, of course you can't see what this is because it's too big. This is too big. We have to zoom out to see what this is. This is the elephant in the room. This is an object that is so big that we struggle to even comprehend it or talk about it. We looked at distance scales in the universe and the cosmic calendar. These are problems we sort of can wrap our head around, but this one is so big and so large that we struggle to talk about it, even though we should be talking about it every day. And this is the human impact on our planet. This has been called a hyperobject. I love that name because it kind of helps you understand the problem. This is a phenomenon that is so massively distributed in time and space and so complex that it defies, in many ways, our human comprehension. So when I talked about solving dark energy and the challenges of getting people to work together and how difficult it may be to solve dark energy, I think this dark energy is a much more simple problem than this one. This is a truly difficult problem. So I want to talk for a minute about the overview effect. We all watched with excitement the Artemis II crew going to the moon. That was fabulous. It was so exciting. Well, there's a psychological effect that astronauts experience when they are in outer space. And I'm pretty sure these 4 astronauts experienced this effect called the overview effect. And it is a profound cognitive shift that will forever change who you are. It is the realization when you go up above the atmosphere and you look down at Earth that you realize that we share this single closed system. For most of us, the Earth is vast and it's grandiose and you can travel forever. But when you go up into outer space, you realize that there's no second home, the Earth is tiny, there's no backups and there's no escape route. And so that is the overview effect. You're getting an overview of the Earth and the position of Earth within the solar system. So I thought we would take a minute and pretend that we were astronauts, because who doesn't like to be an astronaut? And so we're going to try to experience the overview effect, because I believe that in order to truly solve the human impact on the planet, we all need to experience this overview effect. So you're going to look at the Earth and pretend like you're an astronaut. So you're in a rocket and you're looking through this little window. You see the background of stars. And these are the words from an astronaut called Ronald Guerin. He was one of the people who's promoting this effect and describing it and the impact that it had on his life. And so he says, from orbit, Earth doesn't look like a collection of countries, borders, or competing interests. It appears as a single radiant blue sphere suspended in darkness. No lines divide continents. No flags mark territory. Every human conflict suddenly looks small. What is striking is not Earth's power, it's the fragility of the system. And the atmosphere protecting all life is this paper-thin blue halo, barely even visible, and yet responsible for everything that breathes and grows. That is the overview effect, and as astrophysicists, because we work on such large scales, I feel like we have a little bit of that overview effect, which is why I'm talking about it today. But I hope you all tried to experience the overview effect. So the human impact on the planet is massive, and we are unfortunately outgrowing our planet. We don't have a planet B. You can ask Jonathan, he can look very hard for one, but he's not going to find you a planet B. Our most urgent threats are climate and biodiversity. This is the atmospheric CO2 levels as a function of time over here. We stand over here. This is the line where for millennia our atmosphere has never been past these CO2 levels. And over here, this is the human impact on the carbon levels in our atmosphere, which are causing our planet to heat. So you can see this massive spike. The Earth is currently out of balance. Now, over here it says from millennia, atmospheric carbon levels have never been above this line, 800,000 years. But new research from a colleague at UCSC, Professor Poldasar, actually went further back in time, showing that carbon levels may have never been this high in 14 million years. Okay, now we're going to go back to slide 2. When did chimpanzees and humans split apart? What did humans look like 14 million years ago? I'm trying to see who's paying attention. Anyone? What did humans look like 14 million years ago? Well, humans hadn't split from chimpanzees, so we look like that. So it's fair to say that carbon levels have never been this high in the entire history of humanity. That's our impact on the planet, and that is going to have massive consequences. Not on long time scales, it's going to have consequences now. So you have all heard about the consequences of climate change. You know about rising sea levels and greater storms and fires. We experienced them here in Santa Cruz with the fires and the pier breaking and Westcliff Drive falling into the ocean. But one consequence that you may not have heard about, and for me was a turning point mentally, when I first read articles coming in on this, I realized the impact. So I'm going to share this with you in the hope that you might also decide to act. This is a paper from 2022 from Lenton et al. Leauthaud went and looked at the Earth and did something that with hindsight may seem obvious, but the question was, given the warming of the planet, which regions of the planet are going to be habitable? And what's the impact on migration? So the finding is that on the current trajectory, which is 2.7 degrees warming, within 70 years, more than 1 billion people may be forced to migrate away from the equator. This is the trajectory that we are currently on. These regions in purple are regions that are predicted to become uninhabitable because they're just too hot to live in. So we have all witnessed with horror the impact of the radicalization of anti-immigration policies in the United States. But what I want you to think about is how this is going to play out when we have a much larger migration, and in particular the geopolitical tipping points that may cause. And that is the knowledge of sort of this particular research is really what triggered a turning point in my mind of understanding the impact of the human impact on the planet. And then I started to think about science and everything that we do. Well, science, but you can put in any word that you like, medicine, engineering. None of this occurs in a vacuum, right? We don't do science in a vacuum. We rely on a thriving civilization to be able to look for alien life and study dark energy. On the current trajectory of 3 degrees heating within the next 70, 100 years, we are going to be in a world in crisis mode where we will be thinking about food, water, heat management, coastal management, storm recovery, and migration. And we are unlikely, in my opinion, to be thinking about the wonders of the universe and pondering dark energy and dark matter. So I came to realize that figuring out the mysteries of the universe is a luxury. It's a luxury that we enjoy in a thriving civilization in which we take care of the planet and we take care of one of each other, and that enables us to have the luxury of looking out beyond the Earth's atmosphere. So for myself and a growing number of my colleagues, we call it an all hands on deck moment. Here's a New York Times article. Alarmed by climate change, astronomers train their sights on Earth. Because we're really realizing that this is a problem that requires many brains thinking together and everyone's efforts to try to turn the tide. This has real life impact for the work that we do. This is the DESI telescope that brought to you the largest map of the universe today. In 2022, that almost burnt down with this fire. So this is a real threat. Over here, this is an observatory in Australia in 2023 that unfortunately did burn down. And Lick Observatory over the hill also came close to burning down. But these effects are going to intensify, and there will be no luxuries at 3 degrees. So I recently, in the last 5 years or more, started to do a lot more work on sustainability. I'm going to talk about that for just a few minutes. My environmental work is under the slogan, think globally but act locally. I think acting locally is critical, acting within our communities and trying to build local resilience. That's a lot of what my projects are about on the sustainability side. So a lot of this is very hands-on. I work with the students at UCSC. We've worked on irrigation techniques using rainwater tanks. This is an amazing number. Over the past 2 years, we tried to think about how much water you could save and how much food you could grow with a rain tank like this, which costs about $1,000 to install. We have installation videos if you're interested. But this is a pretty cool number. One tank like this, if you're clever about the way that you irrigate, can allow you to grow 600 lettuces in 6 months when we have our summer with no rain. It's probably more lettuces than you're going to eat. Unless you really like salads. So it's a lot of lettuce. So that's really cool. We've also worked on compost designs, because compost going into landfills is an important source of methane gas, which is a greenhouse gas effect. And composting is one really cool local way that you can contribute. Together with graduate student Liliana from the Environmental Studies Department here at UCSC, we are thinking a lot about ultra-local food production. How much food can we produce locally by recycling our own compost and harvesting water? So we're trying to reduce some of the cost associated with producing food locally. This is a paper in preparation that she's writing that I think is really cool. She's taken a map of Santa Cruz. So this is a real map of Santa Cruz with real streets. And she's taken your housing lots and estimated what size of a garden you could have and how much compost you could use locally within your own garden and how much food you could grow locally. And the answer is, the paper is not out, but our hunch is that locally, you could produce all of the greens that you need for anyone who has a decent sized lot, and Santa Cruz could probably produce all of their greens locally. In addition, Lily is tying this in with a new law called SB 1383, which is a California law that requires municipalities to compost all of their organic waste to avoid methane going into landfills. However, a lot of the funding for this is going to very large commercial composting systems, and the ideas that we're working with is if some of that funding could go locally back to you all to help you compost locally and you grow food, then it would be a more closed loop system. And you composting and using your own compost actually is a fairly large sum. For the city of LA, that's $20 million in annual savings. So that's some of my local work. At the front there, I have a flyer with some QR codes if you're interested in learning about some of that sustainability work or getting some of the videos on how to install your own ring tanks or build your own garden beds. We have some videos about that. I also wanted to promote this event next week. Next week is Earth Day, April 22nd. This is a partnership with the art department with my colleague Jennifer Parker. She's organized a fantastic Earth Day festival, 10 a.m. to 10 p.m. on campus. Everyone is welcome to attend. There's going to be all kinds of cool events that she and her colleagues are organizing. And I'm organizing a session at 5 o'clock and at 7 o'clock. The one at 5 o'clock is all about fungi and compost. And the one at 7 o'clock is the inaugural screening in the United States of a film on humanure. If you don't know what the word humanure means, you need to come to the film screening. Or you can come and ask me about it after this talk. So please come next week to this really cool event on campus. Everyone is welcome. I put some flyers, some QR codes out there as well. This is a map of dark matter in the universe on the largest scales. This is what dark matter looks like. This is the wood wide web of the fungal networks in forests. And I put these up here because everything is connected. And the work that we do as scientists is connected with all the life here on Earth. Now, if that's not convincing to you that these things look similar, there's a movie on it, folks. So this movie that just came out, which I encourage you to go see because it's a wonderful movie, Hail Mary, is about astronauts going out into space and encountering space-sized fungi that's eating the sun. So fungi and astrophysics are connected. Finally, to mention an effort that Jonathan mentioned, over the past 3 years, I spent a good fraction of my life writing a giant white paper. It's 120 pages. It brought together colleagues from across the United States and Canada. And it was a thought process. It was an academic exercise of thinking about the different ways that we could restructure higher education to be better suited to tackling some of the challenges that we face with something like the climate crisis or other large crises. And so following this was an academic exercise, but we're now moving words into action. And we're currently forming a new working group on climate action that will be partnering with the United States, Mexico, and Canada. This is really geared towards higher education, so trying to restructure universities, but a key component of this, one of the key recommendations of this was the importance of engaging with the community. And you are the community, and that is a key recommendation coming out of this report. So I want to finish with a vision for the future. I'm a scientist, but I consider myself interdisciplinary and trying to think more and more globally about the connection between the science that we do, but also what is going on here on Earth and what our future might look like. So my vision for the future is the following, is that we all somehow gain a sense of that overview effect. We become more like astronauts and less like individuals living here in Santa Cruz in the United States. We become more global citizens, where wealth is shared among countries and peoples, where resources are used wisely but in moderation, and we live modest but happy lifestyles. Local economies are prioritized, and planetary health and all life forms are respected, and growth is limited. That's my vision for the future. So I love the science that I do. Dark matter and dark energy are so cool, and there are so many more mysteries to be discovered, whether it's inflation, the physics of the Big Bang, alien life. But in order to continue to have the luxury of doing science, and for our children to be able to continue to carry on the work that we do today, we need to act now to preserve the conditions of life on this planet. And continued life on this planet is not guaranteed. And so it is our duty and our responsibility to change our course of direction and steward our planet. And it's everyone's creativity and ingenuity are needed to face these cosmic odds. So I talked about the challenges of figuring out dark energy and bringing people's brains together, and how I've observed that groups of 10, 20 people were really optimized for working on certain problems. Well, this is the hyper-object problem, and we need everyone's brains and everyone's creativity and everyone's ingenuity to solve this problem. So this is the challenge that we face together. So my message for you is the universe is phenomenal. It's beautiful. It's exciting. There's so much to be learned, and we need to act now so that we can continue to study it. Thank you very much.
Thanks so much, Alexie. Really interesting, fantastic talk. We're going to transition to question time, questions for Alexie. We have a microphone down in front, so I encourage folks who have questions to come down to the microphone. The younger people automatically move to the front of the line, so no matter when a young person comes up, they automatically move to the front of the line. So we'll do our first question here.
What does the Great Red Spot look like up close?
I'm going to hand that over to Jonathan, because Jonathan studies Jupiter.
What was the question?
What does the Great Red Spot look like up close?
Wow.
This is much more his field, so I'm lucky that he's here to answer this question.
Well, I haven't been there myself, but the Great Red Spot, is a storm that's been on Jupiter at least 400 years. Galileo was the first person to see it with a telescope in the 1600s. It's like 2 or 3 times as big as Earth across. And it seems to be almost like a big sort of hurricane. It's always sort of swirling around. So I have not seen a hurricane up close myself, but I'm sure some folks probably have. So it's big, fast-moving winds swirling around. Yeah, come up to the microphone. Additional questions, yeah.
How do you get it? First of all, thank you for a fabulous, inspiring lecture, which I really just tremendously enjoyed. Many decades ago, I worked at University of Chicago, and I had the coldest system in the world, a helium-3, helium-4 dilution refrigerator that I held at 20 millikelvin, so 0.02 from absolute zero. Yep. And when I worked with that system, I then zapped helium nuclei, alpha particles, through, and got vortices forming that were quantized, which I think will be found eventually for black holes as the micro and macro. And that system of the two superfluids was theoretically the best example on Earth of a system approximating motion of particles during the Big Bang from the two, the lack of viscosity, the lack of attractiveness, the smallness of the particle. Okay, so when I'm fantasizing about dark matter and dark energy, I've always, even back then, in my own beingness, I hypothesized to myself that black holes would be singularities of absolute zero, even understanding by the second law of thermodynamics that seemingly is an impossibility, but just looking at the collapse of matter and the densities involved at that point. And I've always looked at, maybe it's the feminine, as black holes as birthing funnels into other dimensionalities. And what I just, I don't know, I keep playing in my mind with this birthing hole of these matter collapsing in, but then expanding on the other side, like fourth dimensionality or by string theory, and into a, I believe the Big Bang was, how hot was that? Millions of degrees? Or,
infinite temperature.
Well, right. And so when I think about that, I think about these birthings into the next dimensionality of the matter that has collapsed, that's pulling in everything gravitationally, being spewed into another dimensional space of both new formation of matter and new little big bangs all over the place.
Yeah, let me do a little demo.
And so,
Do you have a
so
pen?
tell me why that's a bad
Does
theory.
anyone have a pen? I'll do a demo. I'll do a demo anyway. So you talked about how black holes might be a connecting channel. That's a really cool idea that is one of those ideas that may almost never be testable. And there are ideas about wormholes, and a wormhole is the following. I like to do this with a pen. Hello? Okay. I like to do this with a pen, but a wormhole would be the following. You take space-time, imagining space-time as a two-dimensional surface, and you imagine space-time being curved, and then you take a pen and you poke a hole through this. In my lectures, I usually have a pen. Okay, so you take a pen and you poke a hole. Oh, yes, great. Okay, so you take a pen and you go like this. It's very dramatic. This is how we do astrophysics in the era of budget cuts. So, this pen is a black hole. And what you said is maybe a black hole is not a point, it's a conduit. And so maybe a black hole is a conduit where you could go from one side to the other. And this is used all the time in movies. So instead of having to travel this long distance all the way from here to here, you take the shortcut through the black hole. Now you can do that in Interstellar, you can do that in movies, but this may be one of the things that we can never really test. So it may be one of those cool ideas.
Could you ever test the quantization of energies with respect to black holes?
I don't think we're there yet. To do that, you'd have to create black holes, and I think we don't want to be creating black holes. No. But what we measure for black holes currently is more related to size, like how big they are and how fast they rotate. Those are two of the, and how they interact gravitationally. We've seen this as being a huge discovery. This is a different lecture by a colleague of mine. It's not my field, but a huge discovery in the last 5 to 10 years has been the fact that black holes collide and they come together and they merge, and we've seen signs of that in the gravitational waves that they emit.
I was looking at the magnetic properties in my work of the black hole, of the quantized vortices that I got, and I don't know if that's a way of approaching it either, but I just felt like sharing.
Thank you. Yeah, that's my colleague Enrico's work. Thank you, thank you.
Yes, are you familiar with the term timescapes as it relates to dark energy?
No. Tell me.
I'm not sure of the lab, New Zealand, I believe, recently published a series of measurements that suggest that the accelerated expansion of the universe is not really happening. What is being done is the standard measure of how the universe is expanding with standard candles. You're making an assumption that the universe on the grand scale is uniform. But the vast spaces where there is no matter or very little matter, those spaces, time occurs differently than in areas of dense matter. So
I did see those results. So I'll comment on 3 facts. One, the first is that the results that I showed from DESI, the results on dark energy, to be crystal clear, they come about because we combine them with results from supernova to get better constraining power, and that's actually what gives us the strongest constraining power. That comes back to the idea that we need to work together with other teams, and these combinations become incredibly complex. So that's point number 1. Point number 2 is I did see results suggesting that inhomogeneities in space, in particular, we call them voids, regions with no matter, could help explain that effect. I saw that in the news. But I ran that idea by some of my colleagues, and they said, well, we already create simulations. We have very large simulations that involve lots of dark matter, where those effects are included, and we don't think it can be that significant. So, but there is a debate, a raging debate going on about all of these ideas and what could explain these results. That's why there's that 1,000 citations, and I haven't read all 1,000 papers with the various so this is one idea among many. But next week, I'm going to a theoretical conference on the physics of dark energy where there will be lots of new ideas. And so when I'm invited back again, I can tell you all what came out of that conference and some of the good ideas that emerged. I don't think currently there's like a leading theory.
okay.
Yeah.
Thank you.
Yeah.
Yeah, go ahead.
Hello. I know thermodynamics, the laws rule out perpetual motion, but if those aren't built using dark matter and dark energy as factors and they affect gravity and motion, could those make perpetual motion at least more likely, if not fully possible?
That's a great idea. It's fascinating because I have a son who's 13 years old. And for 13 years, well, maybe 12, he's been fascinated about perpetual motion. So you should talk with him. But he's been trying to make a perpetual motion machine for a long time now. That's a great question. I don't know how to answer that one. But we do think that on the larger scales, the universe has energy and momentum, and it is expanding, but we think on the larger scales that energy of the universe is conserved. And if energy is conserved, then I'm not quite sure how to answer your question. But yeah, perpetual motion, I guess the universe in some sense is in perpetual motion. If we go through the big rip, then the universe just continues to coast and expand. And maybe in some sense, that's a cosmic analog of perpetual motion. But here on Earth, it's very tricky because we have friction and we have the atmosphere and things that dampen it, like gravity.
Thank you.
Yeah, get in touch with my son. Maybe the both of you will come up with new physics.
What's a star you found that like has the most dark matter or dark energy? Do you like number them?
Yeah, that's a really great question. So we think dark matter is everywhere. So we think this room is full of dark matter. You just can't see it. And in fact, this is not limited to dark matter. There are particles called neutrinos. Neutrinos are a well-known particle, and they are streaming through this room at trillions per whatever. And a neutrino will go through the entire Earth and not even notice that the Earth is there. So similarly, we think the room is full of dark matter, but you just don't have the ability to see it. So we try to use our astronomy techniques to see it. Similarly, we think that there's dark matter in stars. And so there are people, I've read some of these papers and I've talked with some of these people who are trying to understand, if dark matter were in stars, how does that impact how the stars behave? And then what I study more is dark matter within galaxies. And yeah, some galaxies have a lot of dark matter, more than others. And those are questions that we like to think about.
Do you name those galaxies? Keep track of them sometime?
We name them with numbers, 1, 3, 5, 7. But some of them do get famous numbers. But recently, to be more serious, some very famous recent galaxies were actually the opposite, and this was in the newspapers a lot, maybe 3, 4 years ago. People who found little galaxies that seemed to have no dark matter, apparently, and those got nice names.
What about dark energy?
Dark energy is different because dark energy permeates all of space, and it's not concentrated like dark matter. It's more like, the way we like to think about dark energy is the energy of empty space. And one thing I'll throw out there for you and others is that the physics of empty space is actually fascinating. We don't really understand empty space, so there's a challenge for you all. And so dark energy is more the energy of empty space. Think of it as constant and homogeneous. The only weird thing about it is that the universe is expanding. And by expansion, I don't want you to think of something getting bigger. I want you to think of the actual space is getting bigger. So the expansion would be Steve over here sitting in this chair, and you're standing here, and the space between you is getting larger. The floor is expanding. And dark energy is connected because dark energy is the energy of empty space. So the more the floor gets expanded, the more dark energy you have, which is a really weird concept. And it creates accelerated expansion.
Thank you.
Yeah, great questions. Anyway, dark matter, dark energy, very different.
So you use the term, the Great Rip.
Yes.
Is the idea then that space maybe is not infinitely expandable?
I don't know, that's a great question. I use the term Great Rip, but I never study it. But yeah, it's the idea that at some point, the dark energy force could be so extreme that it's tearing apart galaxies. So the force of that expansion is pulling apart stars and could actually rip apart galaxies.
Oh, not ripping space itself then?
Yeah.
But as the space expands, how does its properties change? I mean, is the energy of the vacuum change? I mean, do the virtual particles coming and going change? Do we have any idea?
Right. So hence the mystery of dark energy. So a number that I glossed over, but maybe we can just show the slide so I can show you the number, is one of the greatest mismatches in physics. Where's my slide?
10 to the 220th?
Yeah, the 20th.
The 10 down, yeah.
But let me, where's my dark energy? DESI, dark energy. Oh, here, okay. Sorry, this is the slide I wanted to show you. I kind of glossed over it. It's on the bottom left here. But I've described dark energy as an energy of empty space. But the truth is that doesn't match what we measure. So we can measure an energy of empty space. And over here, that explanation is about 110 to the power of 120 times different from the energy that we measure with cosmic expansion. So this goes back to what I wrote up here. Very few ideas to explain dark energy. So unlike dark matter, where I showed you a whole plethora of candidates, and I have colleagues working on different forms of them, where we have a lot of candidates, dark energy, there's really not many great theories to explain it physically. So then coming back to your question about the Great Rip and the future of the universe, including that slide where I showed maybe we're going to coast, we can't really make a prediction unless we understand the physics of it. Now there is, I'll give you one cool explanation, but there are some ideas out there which are fairly compelling that say that maybe dark energy is not an energy of empty space. Maybe it's a breakdown of the laws of general relativity. So we think general relativity holds the universe together. Those are the laws of gravity. But maybe the laws of gravity are different on larger scales, and therefore the expansion that we measure hasn't accounted for different laws of gravity. That's one of the angles for dark energy, in which case it wouldn't be an energy of empty space. It would be gravity is different. Yeah.
We'll go for one more question, and then we're approaching 8:30. So,
why does matter annihilate when it meets antimatter, and what does that mean?
That's just how physics works. So matter and antimatter meet and they annihilate into energy. What does that mean? It means that when a proton and an antiproton collide, they create light. And so one of the big mysteries, which is, you notice this is the one that I didn't talk about, although I touched on most of the other ones. One of the big mysteries is why we live in a universe that has so much matter. So everything around you here is regular matter. There's very little antimatter, because when antimatter is created, it annihilates and disappears. But the early universe, the Big Bang, so the early universe worked like following. There was a period of inflation where the universe expanded incredibly fast. Then that energy transformed into a sea of particles. That sea of particles should have contained equal amounts of matter and antimatter, which should have then annihilated, leaving us with an empty universe. But for some reason that didn't happen, and there was a little more regular matter than antimatter, and so we then ended up living in a matter-dominated universe. And that's one of the great mysteries for you to work on.
Thank you.
well, I wanted to thank everyone for coming out tonight. We really had a great time. I wanted to thank Alexie again for such a fantastic talk, and everyone have a great evening.
Thank you.